Today we're going to be discussing trigonometry. So the word trigonometry, derived from its Greek predecessors, has a meaning that translates to the following. It actually means measurement of triangles. And essentially what we do in trigonometry is we study the relationship between the sides and the angles of triangles. Now, trigonometry is first introduced to you in grade 10, and thereafter its concepts is expanded in grade 11 and in grade 12. Now, when you are in grade 11 and in grade 12, you are then assessed on all of the concepts that you would have learned previously. So if you find yourself in grade 11 or 12 and you feel that you actually have difficulty with this section, trigonometry, then I would advise that you go back to the basics, meaning that you come back to this video and start with where we are beginning today. So what we're going to be starting off with is trig ratios. Right, so in order to discuss trig ratios, I'm first going to draw a right-angled triangle. Right, so a right-angled triangle is a triangle which has a 90-degree angle in it. Right, so suppose we have this triangle with a right angle in it, and let's let theta be the reference angle. In this triangle. Right, so let's let theta be the angle here. So this is the reference angle that I'm now referring to. So the moment we have a reference angle, we then have definitions for the lengths of the sides, or for the sides of this triangle. Right, so we say that the side opposite the right angle, which is this side, is called the hypotenuse of the triangle. We then say that the side opposite theta, so meaning this side, is actually called the opposite of the triangle. So the side opposite theta, which is your reference angle, is labeled opposite. And the side that is next to theta or adjacent to theta is then labeled the adjacent side. Right, so given a triangle with reference angle theta, and where this triangle is a right angle triangle, we then have labeled our sides by hypotenuse, opposite, and adjacent. That's important to note. So once we have these definitions in place, we can then talk about ratios. Right, so it turns out that the ratio opposite over hypotenuse is actually equal to sine theta. In addition, the ratio adjacent, so I'm using shorthand ADJ for adjacent, divided by hypotenuse is actually equal to cos of theta. And finally, the ratio opposite over adjacent is equal to tan of theta. So I've given you three ratios, and I've now explained what these ratios represent, right? So sine of theta is opposite over hypotenuse, cos of theta is adjacent over hypotenuse, tan theta is opposite over adjacent. So when we say opposite over hypotenuse, what would you write down in this ratio? You would write down the length of the opposite over the length of the hypotenuse in this ratios. So it's important to take note of the lengths or the measurements of those sides. Now you may say it might be difficult to remember these three ratios. So it turns out that we have a very good acronym or slogan for this, and that is SO CA TOA. Right? So what does this actually say? SOH, so, tells you that sine is opposite over hypotenuse, and that's precisely what's written there. CA explains that cos of theta is adjacent over hypotenuse, which is precisely what's written there. And TOA explains that tan of theta is opposite over adjacent, which is exactly what's there. So by just remembering this acronym SOHCAHTOA, you will actually then remember the ratios for each of these trig formulas. Right, so another way of actually interpreting this is by placing your right angle triangle on a Cartesian plane. Right, so that's what I have drawn below. So if we had to read off the values here, so if I read off this x value and consequently read off this y value, then observe that that vertex on the triangle can be described by the coordinate x comma y. More importantly, if I had to draw a circle with center origin that passes through the point x comma y, so let me just sketch this, I'll do my best to make sure that it's a uniform circle. Right, so it should have the same radius all around if I had drawn it perfectly, but let's just suppose that this was a perfectly drawn circle. Then observe that since we have a line drawn from the center, and so let me just note this. Right, so we have a circle with center at the origin, right, and it passes through the point xy. So if the center is the origin and we have the point xy is on the boundary of the circle, then the line connecting the origin to the point xy is actually the radius of the circle, right? So that means that in this triangle that has been drawn on the Cartesian plane, in this right angle triangle, the hypotenuse of this triangle has length r. More importantly, so observe that in this triangle, that would have been the hypotenuse if the reference angle theta was drawn there, as mimicking the diagram from above. Right? More importantly, the side that is adjacent to theta will then have length x, and the side that is opposite to theta will have length y. So based on this diagram, assuming that my circle was drawn perfectly, we then have that our trig ratios written above can now be rewritten in terms of the lengths found in the Cartesian plane. So we then see that sine of theta, which is opposite over hypotenuse, can then be expressed as y, because the length of the opposite is y, divided by the length of the hypotenuse, which is r. We then have that cos of theta, which is adjacent over hypotenuse, is then expressed as x, because the length of the adjacent side to theta is x, divided by the length of the hypotenuse, which is r. And tan of theta, which is opposite over adjacent, can then be expressed as y over x, simply by taking the values from the diagram. Now, quite often you will be tested diagrammatically in this nature, where you are required to solve for certain trig ratios, like the ones mentioned, using diagrams from the Cartesian plane. And I have observed in many grade 12 papers that there is always a question of this nature. So since that is the case, I will create another upcoming video dealing just with solving diagrammatical problems. Right, so for now, let's consider an example. Right, so suppose you were given the following right-angled triangle. Right, so there is a right angle in it, and we have two reference angles in it. We have a beta and an alpha. And more importantly, observe that we were given the length of two sides. So we have the length of side MP is 13 and the length of side NP is 5. The question is, what is cos beta? So firstly, let's write down the ratio in terms of our reference angle beta. Right, so before we write down the ratio, let's label what these sides are. So if that is beta, that means that the side opposite beta will then be, which is NP, is our opposite side. Right, so let me label that as opposite. The side adjacent to it, of course, is the adjacent side. And we have the side opposite the right angle is the hypotenuse. Right, so based on that, we know that cos of beta, remember from our acronym SOHCAHTOA, CAH says adjacent over hypotenuse. Right, and looking at the labels in our triangle, what is the adjacent? The adjacent side is labeled MN, and the hypotenuse is labeled MP. So we need the ratio MN divided by MP. That's what we need to solve. Observe that we do have the length of the side MP. We know that it's 13, but we do not know what MN is. So we need to now solve for the length of the adjacent side. Now, what tools do we have at our disposal? So remember, we are working in a right angle triangle. And it's important that when you are in a right angle triangle, you always remember that you have the theorem of Pythagoras at your aid. So I need you to recall and actually always remember this theorem going forward when it comes to trigonometric problems. Right, so the theorem of Pythagoras tells you the following. It tells you that the square of the hypotenuse is equal to the sum of the squares of the other two sides. Right, so given a triangle, let's just say I gave you the following right angle triangle. So remember, this is true for right angle triangles. So if I label the sides A, B, C, then the theorem of Pythagoras tells you in a right angled triangle, we have that C squared, the square of the hypotenuse, is equal to the sum of the squares of the other two sides. So it's equal to A squared plus B squared. So that's important to note. So let's write down the equation, this equation, C squared equals A squared plus B squared, in terms of what we have in the above diagram. So observe that then the hypotenuse MP, so MP squared, equals to the sum of the squares of the other two sides. So it's equal to NP squared plus MN squared. And remember, we are solving for MN. That's what we want. MP, the length of MP is known, and the length of NP is also known. We have 13 and 5. So let's solve for MN squared. This implies that MN squared is then equal to MP squared minus NP squared. So I've just taken that into the other side. So putting in all of the information, we have MP squared is 13 squared minus NP squared, which is 5 squared. Right, so MN squared is equal to 13 squared minus 5 squared. That means that MN is equal to the root of 13 squared minus 5 squared. 13 squared is 169. 5 squared is 25. So we've got 169 minus 25, and we're taking the root of it. So it's the root of 144, and this is equal to 12. So therefore, we now have that MN is equal to 12. So just putting this back into the above calculation, we then observe, therefore, cos of beta is equal to 12 divided by 13. And that is your final solution. So remember, one of the main tools that we used in here was the theorem of Pythagoras. Right, the next thing that I want to discuss is actually trig identities. Right, so what is a trig identity? A trig identity is any trigonometric statement that is true for all theta. Right, so there's no restriction. It's just a statement that will always hold true. So it's a fact. Right, so the two common trig identities that you have to know and you are taught from grade 10 onwards is the following. The first says that sine squared theta plus cos squared theta equals 1. And the second identity is that tan theta is equal to sine theta divided by cos theta. Alright, so we are actually going to prove these two identities. In grade 11 and 12, you are actually required to know these proofs. Alright, so let's prove them. Proof of 1. So firstly, let's draw a right-angled triangle. Right, so let me draw the following. Let's consider the following right-angled triangle. Right, so I'm going to label the sides again. So let me label that A, B, and C. And here's our reference angle theta that's required in those statements. Right, so that's what we have. So in 1, we're working with sine squared theta and cos squared theta. So let's write down what is sine of theta. Remember our acronym SOHCAHTOA, sine of theta is opposite over hypotenuse. Right, so in this diagram, if that's the reference angle, this is our hypotenuse, this side is the opposite, and this side is the adjacent. Right? So based on the lengths that I've written down in here, I've written down lengths or labels A, B, and C. We then say that the opposite over hypotenuse is A divided by C. So that is the ratio for sine theta. Let's now consider cos theta. Right, from the acronym SOHCAHTOA, this is equal to the adjacent divided by the hypotenuse. So from our diagram, adjacent over hypotenuse is B divided by C. So now let's prove our trig identity. Right, the trig identity tells you that sine squared theta plus cos squared theta should equal to 1. But based on our diagram and the ratios we've obtained, let's check if this is indeed true. So sine squared theta is then A over C squared plus cos squared theta, which is B over C squared. So let's now simplify these expressions. So we then observe that this is A squared divided by C squared plus B squared divided by C squared. And once again, we've got a common base, so I can now compute the sum. So this is A squared plus B squared divided by C squared. Right, and let's look at what we have. Remember, I had just gone through the theorem of Pythagoras with you in the previous slide. So let me bring that slide back. Right, so in any right-angled triangle, the square of the hypotenuse, and remember here our hypotenuse is also labeled C, is equal to the sum of the squares of the other two sides. So we have that C squared is equal to A squared plus B squared. So by the theorem of Pythagoras, we then have that A squared plus B squared is actually C squared, and this is being divided by C squared. So we observe that our final answer is 1. So therefore we have shown that sine squared theta plus cos squared theta is equal to 1. Now let's prove 2. So proof of 2. And so we are now proving that tan of theta is equal to sine theta divided by cos theta. So firstly, given the above triangle, so from the triangle, the right angle triangle that we're working with, what is tan of theta? So from our acronym, SOHCAHTOA, tan of theta is the ratio which is opposite over adjacent. So based on that triangle, opposite over adjacent is A divided by B. So now let's check if that ratio, that trig identity actually holds true. Right? So let's consider what is sine theta divided by cos theta. So we've already written down what sine theta is. It is a divided by c. And then we are dividing that by cos theta. Cos theta is b divided by c. So I've got a fraction divided by a fraction, so I'm going to invert and multiply. So that tells me that a divided by c is then a divided by c, which is then in turn divided by b divided by c, is equal to a divided by c times c divided by b. So I've inverted the fraction from the denominator and we've multiplied. Observe that the c's now cancel, and this multiplication now simplifies to a divided by b. And remember, a divided by b is actually tan theta. So we have shown that sine theta divided by cos theta is indeed tan theta. So those two trig identities actually hold true, and we have proven so. Alright, so just a remark before I end. So I want to focus on trig identity number 1. Right, so we have that sine squared theta plus cos squared theta equals to 1. So therefore we can also rewrite it as follows. We observe that if I wanted to write down this trig identity, making sine squared theta the subject of the formula, then sine squared theta is equal to 1 minus cos squared theta. And similarly, if I wanted to make cos squared theta the subject of the formula, then cos squared theta is equal to 1 minus sine squared theta. So these are two additional ways of rewriting the first trig identity, so remember that. Right, so just as an exercise for you guys to try out, prove the following. Show that 1 minus sine of beta multiplied to 1 plus sine beta divided by cos squared beta is equal to 1. And you will require one of the two forms that I had stated above. So maybe just pause the video, take down the question, and then attempt it. So this is where I'm going to end.